Welcome back to our lecture video. In this particular lecture, I will demonstrate a couple of problems selected from the end of section 8.2, and I hope that these problems will help you work on the homework assignment, the book assigned problems, as well as the MSL homework assignment that I will turn on today, that will be due next week. So this will be our second problem because the first one was already included in my lecture video, and to start with, I would like to begin with problem 15 right here. So basically that's just the conceptual problem, not story problem yet. We will work on that later. This particular problem simply states that we have a simple random sample of size 49, which is obtained from a population with the mean of 80 and standard deviation of 14. Let's write that down. So here we have so I think what I'm going to do here is start a new one. Let's do that instead of working on the remaining space. So we'll start a new one, and this will be problem number 15, section 8.2, no 8.1, and I believe it's H. Let's see here. It's on page 404. Okay, page 404. So we are given that the sample size here. Let's write down the information. So info. We are given that the sample size is 49, and the mean value 80, standard deviation 14. Okay, that's the information given to us. Now we ask A, describe the sampling distribution of X bar. So here we are asked to describe and interpret the sampling distribution of the sample mean. That's what X bar is. The distribution of X bar is the distribution of X mean. That's what that means. The sample mean, sorry. And so we have to somehow describe the values of them, and pretty much the equation that I gave you earlier directly apply to answer this question. So here we want to look at the sampling distribution of the sample mean, and the sampling distribution of sample mean has the following expression. We have mu of X bar is ultimately equal to the mean value of the population, and that the standard deviation of the distribution of X bar will equal to the standard deviation divided by square root of n. Clearly, you see here the mean value is given to us already, so ultimately the sampling distribution will have a mean of 80 and a standard deviation of 14 divided by the square root of 49, or 14 over 7, or 2. Thus, the distribution of the sample mean has the following properties: that it has a mean value of 80 and a standard deviation of 2. So that pretty much answers question A. And now it asks us, what is the probability of computing a mean value that is greater than 83? So B is asking us to compute this probability value right here. Now, again, I'd like to remind us that here we are computing a group of numbers at the same time. And the reason is that you see here, instead of a single observed value, it is a mean value of a certain set of samples. So here, if you don't fully understand the difference between the sampling distribution and the general distribution that we looked at earlier in the previous chapter, you can see that if you do not fully understand what x bar means in relation to this probability value, then you wouldn't be able to determine the difference between this probability that deals with a set of values at the same time and a probability that we dealt with in chapter 7 that only regards a single value one at a time. So that's the key here for us to understand, and the equation that requires us to compute the z value. Remember, this is a general description again of a distribution which refers to what we call the general distribution of the sample mean. And in fact, you can even draw that curve based on the information that we just found in the first part. So let's just draw that curve. Okay, so here we have a normal curve that has this value right here. So this is what we call the x bar distribution. Okay, and here you have 80 and then the standard deviation of 2. Now we need to find the probability that it is greater than 83. So if this is 82 right here, then 83 will be somewhere around here. So this is basically you can see here the first standard deviation is 2, then the second standard deviation will be increased by another 2, which is 4. So 3 is somewhere in the middle between 2 and 4, which is right here. And this is what we are looking for. We're looking for this region. We want to compute the probability of finding the mean value that is greater than 83. And now this is a general curve. It is a normal curve, but it is a general curve because it has an arbitrary mean value. This is not just a single mean value. This is the mean of the sample mean. So we have to perform the translation equation, and that is based on using this new equation that we just derived in this chapter, which has the mean value minus the population standard deviation divided by the standard deviation over square root of n. So here you have x bar minus the population of the mean value of the population divided by the standard deviation over square root of n, and that will give us the z value. That will give us the z value. So what we have then is this curve that looks like this. Again, oops, that looks almost like a skewed left curve, and we don't want it to look like that. It is basically a normal curve, and it becomes a standard normal curve that has a value in the mean, which is the mean value equal to 0 at the center for the z. And let's compute that. So I'm going to start a new sheet for us and then start at the very beginning. So the very beginning is at, well, let's say for part B, we want to find the probability of finding the mean value that is greater than 83. That's what we want. Okay. To do that, we need to find the z. We need to translate this into the z. So our z value is based on this expression, which is the mean value minus the sample mean minus the population mean over the standard deviation of the population, and then divided by the sample size. So here we have 83, that value there, minus mu, which is 80 if you remember, and then the standard deviation is 14, and then the sample size is 49. Okay, so the sample size is 49. So basically we found this already. In fact, if you remember, in fact we don't have to compute this, recompute it, because we found already, which I should mention earlier, we found that the standard deviation of the sample mean was 2. Okay, and that was because you have 14 divided by square root of 49, which means 14 divided by 7 equals 2. So you basically have a 3 over a 2, or a 1/2, 1.50 to be exact. Thus, our probability based on the z value is now determined to be, we have x bar, let me rewrite this one more time, x bar greater than 83 equals the z, which is greater than or equal to 1.50. Okay, let me explain this in a moment, but first let's draw this curve right here, the general curve associated with the probability of the x bar. So this was, I think it was 80 and 82, 84 and 83 is right here. This is the region that we are interested in finding. Okay, and then with the equation based on the z, we're able to translate this into this standard normal curve, and the normal curve tells us that we have a 0 here, a 1, a 2, and a 3. A 1.5 is somewhere here, and the region we are interested in computing is this one right here. So obviously you see here, it's basically reflecting the original region and the original curve, except that you have the standard value to compute, to be based on. What that means is that here with the standard normal curve, you have a constant standard deviation. The mean value is always 0, the standard deviation is always 1, and that's why we need to use the table in the back of the book, which is table 5. Okay, now let me explain this right here. Now originally we are computing the probability of a mean value that is greater than 83, okay, which means anything that is greater than this line right here. Now when we translate into the z value, we could have just written like this too. I could have done that way too. But the problem is this, that it doesn't matter whether we are talking about including a region along this line or a region to the right or to the left of this line. In fact, we are interested in finding the region to the right of this line. And the reason why we use this equality sign is that, you see, for a general distribution, if we're asking a question, what is the area along this line at 1.2, let's say, okay, and the answer is 0. So you see here, if we are interested in only just the probability value or the area along this line, it's 0. And what that means is that it doesn't really matter whether we use just the greater than sign or the greater than and equal sign, it still be the same. So that's why it's always customary for us to include that line as well, even though there is no value to be included, but we write it like this. So now I think I made a point to explain this earlier in chapter 7, but now I want to make it clear one more time so we can understand it. Why originally we had only the greater than, and then suddenly when we computed the z value, we include the equality. Well, the reason is the following: what I just explained earlier about that the area along that line is 0. So therefore, it doesn't really matter whether we include or not include that area. The area of the value of the area to the right is still the same. Okay, so now it becomes a little bit messy. Now let me start one more sheet to show us the complete calculation of this. So here what I have done was basically able to write the probability of x bar now, which is greater than 80, to become in the z expression, which is a 1.50. I include 0 because for the z value we can look up the table up to 2 significant figures. So this curve you already saw it, which has this expression here. I mean the region here corresponding to this expression, which is, let's say, is a 1 and a 2, a 1.5 is somewhere around here, and this is the region we're talking about. Now, there are two ways to compute this. You see, if you look up the table 5 to read the value, you cannot really do that because the table only gives us a means to read a value from negative infinity to a certain value that is to the left of the z value. See that? Even for the positive one. So this is a negative, and what for the positive one you still, well, actually this curve here doesn't give us that, but I think the one in the book that shows us both sides, the negative and the positive, will give us that curve. But this one here, you can see if it starts from above 0, which is from the middle, it still reads from negative infinity to the positive value to the left of z still. So that means that you cannot just read the table, look up the table and read the value and then give you and then report the answer. That answer will be wrong because you give the wrong answer. The table does not give you a region for this one. So you need to come up with a method to do this, and there are two ways that I've shown us how to do this in chapter 7. One is to use a symmetry argument, and that is to apply a mirror image. And the symmetry argument claims that if you place this curve in front of a mirror, okay, this is a mirror right here, and it will appear like this in the mirror. So this is the reality and this is the real image. So what that means that you see here, the region starts at to the right of the z equals 1.5. Now it becomes the region that starts from, that goes to the negative, to the left of a negative 1.50. So the probability of the z greater than or equals to 1.5 now becomes the probability of z less than or equal to negative 1.50. This is what symmetry argument gives us. And now I can use this to look up the table, because right now you see here my expression exactly resembles the expression that the table provides, which is z now is to the left of a certain value. Alright, so I'm going to the table and then just read that. So a negative 1.5, which is right here, negative 1.50, the first column provides a 1.50, which is 0.0668. That's the value, 0.0668. So that is from symmetry argument or mirror image, 0.0668. Okay. Now there's another way of doing this, is to use the complement. The complement, so here's a complement rule. The complement rule tells us that if you have a region to the right of a certain z value, like this one right here, then you can take 1. You can take 1, which is the entire curve. The entire curve is 1 minus the curve that reads from negative infinity all the way to the area to the left of the positive z. So here you have a 1.5 right here. So this is the region that we are interested in. So the expression is basically 1 minus the probability of z less than or equal to a 1.5. So now you can see here I can look up the table again, because here we are interested in the area to the left of a certain z value. The less than and equal to equality here is the one that expresses the region to the left of a certain value, which is 1.5. Now let's look up the table, and the table also allows us to read that, and a 1.5 is in the positive region, which is right here. So a 1.5, the first column again is 0.00, so here you have a positive 1.50. So here the value is 0.9332. 0.9332. That is the region. That is the region that describes this entire curve here to the left of a 1.5 value. So here you have a 1 minus 0.9332. If you take a 1 minus 0.9332, you get this answer. So you can see here, simple arithmetic shows us that you have a 2 minus from a 0, and that's a 10, so there's an 8, carry a 1, which is 4, 10 minus that is 6, carry 1 again, 6, and then carry 1 again is 0. Okay, because you have a 9 here minus a 9, that's a 0. So the answer is still the same. And you know what? Preferably this is a quickest approach. So you might as well learn how to apply this method. So this is 0.0668. That's for part B. Okay, and before I move on to the next part and the last part, I'm going to give us the video code, which is 0.0668. That is our video code. So let's start with the next part, which is part C. Okay, and I'll just get rid of this one here because we don't need it anymore, and this one too, we don't need it anymore, and that should be good. Well, this one too, I suppose. Okay, so well, maybe this one also to clear all the messy look. Okay, the next one is, what is the probability of computing a mean value of less than or equal to 7.58? Okay, so well, this is an easy one. Why? Because we are already interested in the area to the left of a certain x or z value, which you can read the value of the table in table 5. So here we are to compute the x bar less than or equals to a 75.8. To do that, we have to translate this from the general distribution to the standard normal distribution. And again, you see there was a question to explain why do we need, you know, the question from exam 2, the definition question, why, or not exactly definition question, which a lot of people express it that way, which I disagree. It is basically the meaning of the actual expression of the translation of the normal curve to the standard normal curve. And that is, what does it mean, the meaning of that translation. So the meaning of that translation is that we translate from the general curve to the standard normal curve so that we can use a table. So here you have an arbitrary value, and now you have a standard value that always begin with 0 as the mean value, and then the standard deviation is always 1 to the left, even 1 to the right. Okay, so that's why it's purely symmetric. And so what we need to do then is we need to convert this using the z score, or what we call the standard error equation. So now we want to re-express this in the z value. So I'm going to do this quickly for us. You see here, if you remember, the x bar is related to the z with this expression right here. And of course we already found this, okay, to be 2 from part A. So I'm going to express them, put it like this. So here you have a 75.8 minus 80 divided by 2. Okay, and if you do this by basically taking the difference and then compute the value by dividing by 2, okay, you will have a negative 2.10. Let's just double check that quickly. I think I have my calculator somewhere here, right here. So we'll so here, let me close this here. So we have a 75.8 minus 80 divided by 2. And that gives us a negative 2.10. Okay? And that's our z-value, which is to the left of it is the region that we want to calculate. Oh, by the way, I think I made a mistake here. I did it wrong. Let me rewrite this one more time. There. I did that by mistake. So it's like this. There now. We get the right expression. And if you look up the table, let's go back to the table. We are looking for the z equals or less than a negative 2.10. So let's go to the table. A negative 2.10 is up here, right here, a 2.10, and a 2.10 is this region right here. A negative 2.1, and the first column is 0. Yeah? So the value is a 0.0179. That is the answer. 0.0179. We can interpret this result too. So the interpretation of this is that the probability, for example, let's say if we take 100 or even 1,000 random samples of n equals 49 from a population with mu equals 80 and standard deviation equals 14, then roughly 1.79% of the sample with a mean that is less than 75.8. That's what that means. That's our interpretation. Okay. Let me write this one more time. So here's the interpretation for this result. It means that if we take let's say 100 samples or even 1,000 samples if you like, okay, of n equals 49 with sample size equals 39. So here let's say it was supposed we take 100 samples of size 49, okay, from a population with mu equals 80 and standard deviation equals 14. Okay, then roughly 1.79% of the sample, 1.9% of the sample will be with a mean that is greater, that is less than 75.8. Okay, that is the interpretation of that result. Okay, so now let's finish our last part, which is part D, and that is to compute a probability between 78.3 and 85.1. Okay, now you see here the way that we compute. That's why I mentioned back in chapter 7 that the skill we learned back in chapter 7 is very powerful and extremely useful and practical and important, to be exact, that we will be using that skill for the rest of the semester. And that is to use a table, learn how to use a table. And the only difference here is that we only need to compute the x bar translated to the z value using the standard error equation. The rest is the same. So for this problem right here, part D, we are looking for to compute the probability of finding the mean value that is between 78.3 and 85.1. Well, again, you see here we need to find the z-value corresponding to the 78.3, the z-value corresponding to 85.1, and let's call this x1 bar, and we'll call this x2 bar. And now we will be computing the z1, which is associated with the x1 bar, like this. And then the z2 associated with the x2 bar, like this. Okay, so here you put in the value, you have 78.3 minus 80 divided by 2, and here you have 85.1 minus 80 divided by 2. And if you compute this carefully, you will see that basically pretty much, well, you know what, let's do that together, because I'm working on this starting from scratch too. So we'll start with this here. So we'll have the, oh, I need to turn on the calculator. So we'll have a 78.5, oh wait, 78.3. Okay, so I have 78.3. Let's double check the value again. Okay, that's 78.3 for the first equation, right? So 78.3 minus 80.0 divided by 2. So minus 80.0 or 80. Oops, I think I did it wrong. Let me minus. Okay, what happens here? I think sometimes my calculator, because of the simulation, so let me clear that. So I'm gonna clear the whole thing. I guess maybe something is, you know what, let me turn that off. If it doesn't respond, let's just close the whole thing. Okay, and then I'm going to go back and load up a new calculator. Let's see here, where is that? I think, you know, I probably don't have that. Let me go to my file one more time and open that. Okay, and so let's turn it on, and we have a 78.3. Oops, I need a parenthesis. 78.3 minus 80 divided by 2. That gives me a negative 0.85. Okay, so, well, before we do that, let's I'm going to bring up the entry, and oh, that's wrong. I'm going to bring up the entry one more time, and then I'm going to change this to 85.1, right? Okay, so I can compute both numbers at the same time. So here I have a negative 0.85 and a 2.55. All right, those are my two values: a negative 0.85 and a 2.55. So a negative 0.85 and a 2.55. So now pretty much this is what I'm going to get. A P of Z equals a negative 0.85 is less than or equal to a Z variable that is less than 2.55. So that's what we want to compute. And now if you look at the curve, oh, that's a kind of a strange curve. Let me draw to make it a little bit a normal curve. There it goes. So here you have a 1, a 2, a 3, a 2.55 somewhere around here, and a negative 0.85. It is a negative 1 right here, negative 2, negative 3, so a negative 0.85 somewhere around here. This is the region that we are interested in computing. That is a 2.55 and a negative 0.85. Okay, One way of doing this is to split the curve by reading a value from negative infinity all the way to a 2.55. Right here, this entire region, a 2.55, minus a value read from negative infinity all the way to a negative 0.85. Right here. I always draw the middle line to mark the zero spot, so that I can eyeball the position and then make a value look appropriate in scale. So this expression right here is P of Z less than or equals to a 2.55. Now this expression allows me to read off the value from the table. The same for this one. I have a Z less than or equal to a negative 0.85. Okay. Look up the table for a 2.55. Right here, a 2.55 is, well, let's check the column. So the first column here is column 1 is 0, 0. Column 2 is 0.05, 0.01, 0.02, all the way to 0.05. So column 0.05 is a 6th column, right? So that we know. And now I'm going to go down to a 2.5. So a 2.55 is going to be on the 6th column. 1, 2, 3, 4, 5, 6. So 6th column is right where my arrow is pointing to, right there. 0.9946. That is the answer for the first curve, right here. Actually, well, you know what? I could probably squeeze that value in here. 0.9946. That's what it read. Okay, 0.9946. The second curve gives us a negative value, right? 0.85. So a negative 0.85 is up here, right here, and again 0.85, which is under the same column. So you got column 1, 2, 3, 4, 5, and 6. So a 1.977. That's the value that I get. So a 0.1977. Let's write that down. 0.1977. The difference between these two will give us. Let's do this. Well, let's just subtract. As you can see here, I subtract a. So the first one is going to give me a 6. Let me do this. So a 6, and then we carry a 1, an 8, an 8. That's going to give me a 6 again, 6 minus, and then carry the 1 again, and that's going to give you a 0 and 10, that's a 9, and then we carry a 1, and a 1 over 1, that's 2, 2 from 9 is 8. Oh wait, there's 7. That's not right. This is the first one. Is okay. I think I did it wrong. Hold on. This one here, a 16 minus a 7 is a 9. Alright. And then 6. And then that's going to give me a 9. And then a 7. There. So the answer is 79.69%. So the interpretation is that if we select a sample, let's say 100 sample, then we know that about 79% of them will have the values between 78.3 and 85.1. That is the interpretation of this expression. And that concludes this example. I'm going to cut it short at this point and give you another lecture video that talks about a couple of other problems, word problems, so that you also know how to solve them to work on the homework assignment for the book assigned problems as well as the MSL for this week. Thank you.